This is Lecture 6, Part 5, where we are focusing on high-intensity sweeteners and their use in the food product reformulation or modification process. Obviously, high-intensity sweeteners are another alternative to sucrose. What we know about them is that their relative sweetness compared to sucrose varies, but it is high, meaning we need very low concentrations. We also know that there are now both synthetic and natural possibilities, and approval has been received for both. In addition, each of the possibilities has unique characteristics, and those characteristics may ultimately be a deciding factor in the choice made among your alternatives. But we also know some other facts, and those include that high-intensity sweeteners do not provide bulking, do not participate in fermentation reactions, do not participate in browning reactions, are not involved in moisture retention, have no effect on texture, and do not help control water activity, all of which are potential functional roles of sugar in food products. What does that mean for us? That additional ingredients will have to be incorporated to carry out the functions if necessary in a particular product. Splenda is a good example of a way the food industry has attempted to deal with this on behalf of the consumer. Splenda, in fact, is a combination of two key ingredients: sucrose, the high-intensity sweetener that only provides sweetness, and maltodextrins. And the hope is that the maltodextrins will carry out any of those additional functions of sugar that would be necessary in a given food product. The data in this table are similar to the data used to generate a sweetness profile. And I've included sucrose as a point of reference in the first row as we go through the table. Other possibilities are listed in the first column. In the second column, the relative sweetness at the same concentration of all of these potential sweeteners is indicated. It's pretty obvious. Low concentrations will be needed of the alternatives. The third column tells us at what point maximum intensity is reached once the sweetener makes contact with the taste receptors. That suggests that there will be differences in onset time, and for most of the sweeteners, it's a longer point to onset. Sweetness duration. This is temporal persistence. It is longer than sucrose for all of the alternatives presented here. That's always an issue with high-intensity sweeteners, and typically a negative. In the next column is some background information to let you know how long these products have been around. And finally, in the comments column, there's some information related to additional factors that you need to consider when choosing an alternative, depending upon the particular food system in which you are incorporating that alternative. In particular, note that temperature is indicated. So you're going to need to consider temperature reached during processing or cooking. Is the product stable at those temperatures? In addition, you're going to need to consider the pH of the food system. Again, is your alternative stable within the pH range that exists within that particular product? Here are a couple of additional alternatives. Note that once again, neither matches sucrose. And in the case of aspartame, we have a product that is not heat stable. That means it can't be used in products that's heated. It breaks down. When it breaks down, it's no longer sweet. Currently, the multiple ingredient approach is being used when products are reformulated with sugar alternatives, and this graph indicates why. Let's look at the individual lines on the graph. 3, or the pink line, is sucrose. That's the line we want to match. In this case, the concentrations have been adjusted in an attempt to get the same sweetness intensity. Line 1, the peak of the curve, is pretty much the same height as sucrose. Line 4, the peak of the curve is pretty much the same height as sucrose. We've achieved the same sweetness intensity. Line 1 is ACE K, line 4 is aspartame. However, those two lines do not sit on top of line 3 or the sucrose line. There's not an overlay. They differ. Doesn't have the same profile as sucrose. But look at line 2. That's the green line. It in fact is an ACE K aspartame blend, and it pretty much sits in the same area of the curve as the sucrose line. Yes, it's sweeter, but that can be fixed. You simply adjust the concentrations. What these data show is that blends do a better job of mimicking sucrose than do the individual high-intensity sweeteners. They're synergistic. As a result, combinations of high-intensity sweeteners are often used when reformulating food products. Look at your ingredient list and see what you find listed. In summary, any sugar substitute has to provide sweetness. It's a key role of sugar in food products. And depending upon the food product, other functional roles may apply. It really depends on the individual product. Sweetness is actually, in the whole scheme of things, pretty easy to mimic. The other roles are much more difficult. So that makes beverages one of the easiest products to reformulate. Other products remain a formulation challenge. In summary, when selecting an alternative ingredient, whether it's a sugar alternative or something else, it is important to remember that a single ingredient may serve multiple functions in that food product, and all of those functions must be considered. Finally, it is the desired final quality of the product that determines the ultimate selection among ingredients available to you. It will eventually be the consumer who determines whether or not you have met their quality standards. To do so, it means that you need to know the functional role of each ingredient and what the gold standard is for a given food product. Our next topic is to look at the steps in that reformulation process.